Hi, morning guys. Welcome back to Physics 145, Tutorial 4. Okay, look at Tutorial 4. Question 1. Define work. Oh, sorry, not Tutorial 4, Tutorial 5. Okay, Tutorial 5. Question 1. Define work. So work is defined work. W is defined to be the dot product, okay, the dot product of the force, okay, applied to an object with the displacement of the object. Okay, so work done is equal to F dot S. Okay, F dot S. So that is the definition, okay, for work done. All right. Okay, number 2. Write the mathematical equation of the work. Okay, we already have this, but this one we still need to expand it. Okay, let's imagine you have an object on the floor. Okay, we assume at the moment there's no friction between them. Yeah, so let's assume the object is applied a force F in that direction and it moves with a displacement S, and the angle between them is theta. All right, so the work done, as we know, the definition is F dot S, but we know that that dot product gives us this. Okay, the magnitude of force multiplied by magnitude of displacement and then multiplied by the cosine theta. Okay, and normally we just simply write down without the vector sign Fs cosine theta. So that is the equation that we are using all the time. You even use this one in your, I believe in Form 5, right? Okay, without realizing it is a dot product. Okay, next one, number 3. So number 3, give 2 types of potential energy. Okay, potential energy got 2 types. All right, so I will do in a box form. So the first one is the gravitational potential energy. Okay, the gravitational potential energy. Normally we use a symbol EP. Okay, EP. And then the next one is the elastic potential energy, or spring potential energy. You can also call elastic, okay, or spring potential energy. Okay, elastic or spring potential energy. Of course, it got something to do with elastic material. So this one can be divided into 2 types. Okay, 1, 2. Okay, gravitational potential energy, and for the spring, normally we can use ES or EE, but ES is more suitable. So you try to use logical step when you assign something to certain type of quantity. For example, E always stands for the energy, so the subscript will tell us that what type of energy is referred to. This one is sometimes we EP, because EP is the first one, so we use potential energy. We always refer to gravitational potential energy. Okay, okay, so that is question number 3. Next, question 4. Okay, our question 4 asks for, figure above shows a 45 Newton force is used to pull a 5.5 kilogram object across a rough horizontal plane. Given the mu value is 0.4 and the object moves with constant acceleration for a distance of 8.7 meter. Constant acceleration, yeah? So compute the frictional force. Okay, compute the frictional force. And then the work done by the force, and then the work done by the frictional force. Now, I suspect, okay, that it's not, okay, it's not constant acceleration, but never mind, we just go ahead with that. Okay, so we draw that diagram in order to help us to understand the situation more. So this is a rough floor. Then we have object. Then we have a block on the floor. And then a force is applied to it at 35 degrees. And this force is 45 Newton. And the horizontal line is here. And this angle theta is 35 degrees. So the surface is rough. So we have a mu value of 0.4 given in the questions. Now first, we calculate the frictional force. So to calculate frictional force, you have to label. Okay, we have to label all the non-forces. Okay, so number one is the weight. Okay, the weight, and then we have normal reaction N, and the weight is W. Now other than that, we know that also our force F can be split into two components. Okay, it can be split into two components. One is this, okay, vertical component. I'll call it Fy. Another one is the horizontal component, which is the one that accelerates the object. Okay, is the one that accelerates the object towards the right hand side. Okay, this one I will call Fx. Okay, so now our normal reaction is used to calculate our friction. So that one you have to be very careful. It's not simply the normal reaction which is equal to weight. Yeah. Okay, so first we know that our friction is equal to mu n, right? Okay, mu n. But if we look at our blocks here, when we consider vertical motion, okay, when we consider vertical forces, okay, when we consider vertical forces, the total vertical forces must equal to 0 because the block is not moving up and down. Yes, it moved to the right hand side, sliding to the right hand side, but it's not vertically up and down, so it stays the surface all the time. So n plus Fy plus W must equal to 0. So we have n plus Fy plus negative W must equal to 0. So we have n is equal to W minus Fy. And your Fy is equal to F sine theta. We can calculate that one first. Okay, so or you want to put this one in also can, no problem. Okay, we can put that one into the equation there. So this is our normal reaction. This is how we get our normal reaction here. Okay, so now we're going to put this one into here. So our friction become mu W minus F sine theta. Okay, so now we can put in the value. This one is 0.4. What is the mass? The mass is 5.5. Okay, 5.5. 5.5, and then the gravitational acceleration is 9.81. Okay, mg, minus the force is 45, and the angle is 35 degree. Okay, so let's calculate this. 5.5 times 9.81. Okay, and then minus 45 times sine 35. Alright, we have this one multiplied by 0.4. Answer is 11.26. Okay, 11.26 Newton. Alright, that is our answer for the first one, friction. Then the work done by the force. Okay, work done by the force. Okay, when it mentioned work done by the force, is a work done by this force, the F. Okay, so there's number 2. Work done by the force, big capital letter F. So the formula is F dot S. Okay, so we have Fs. If you look at the angle between them, it is 35. So we have cosine theta here. This one will be 45. But we need one more thing. What is the displacement? Okay, what is the displacement? We don't know, right? So we have to calculate the displacement. So we are given that, already. The displacement is given. Move with constant acceleration for distance 8.7. So we know the displacement here. So we multiply 8.7 and then cosine 35. Okay. So I have 45 times 8.7 multiplied by cosine 35. Answer is 320.7. Okay. 320.7 joule of work done. Alright, so that is number 2. Next one is the work done by the friction. Work done by friction is F dot S. Now, you have to know that friction is in the opposite direction. In this case, it will be here. Because friction is always against the direction of the motion of object. Okay. So displacement is to the right, friction to the back. Right? So you have angle 180 between them. Okay, 180 between them. Eh? So this one is going to be Fs cosine 180 degree, and it gives us negative Fs. So negative Fs, that is negative friction already have 11.26 multiplied by 8.7. So 11.26 times 8.7, the answer is 97.9 negative joule. Okay, 97.9 joule. Negative must be in the answer, then no negative, so you should put a negative in, because the work done by friction is normally losses, will be lost as heat. Okay, so that is question number 4. Next one, page 2, question number 5. Okay, question number 5, state work energy theorem, okay, or work energy principle. So work energy theorem states that, okay, the work done on a system, okay, is equal to the change in its kinetic energy. Okay, so that means whatever you do on a system, work done is equal to the change in the kinetic energy of the system. Or we can write like this also, final kinetic energy minus initial kinetic energy. That is the work energy theorem. But in a simple system, sometimes we can apply it to potential and spring potential energy as well. Any other energy work done, right? But the most accurate one is for referring to kinetic energy. Okay, that's number 5. Okay, go to number 6. Waffy pushes on a wall. Explain why the work done by Waffy is 0. Okay, so you can see that don't know what happened to this Waffy, why I need to push a wall. Now this is the wall and this is the floor. So Waffy, okay, is pushing the wall. Okay, so that means Waffy is actually applying a force. Okay, applying a force to the wall. We call this one F. Okay, but it seems like the wall is actually not moving. Okay, so the displacement is 0. Okay, displacement is 0. So we go according to physics. Okay, work done by Waffy, not wafer, Waffy, W is equal to F dot S, okay, which is equal to Fs cosine theta. Okay, so F is a certain value. Yes, you, no matter how strong you push a wall, unless the wall collapses, or else when your displacement is equal to 0, no matter what angle you have, your answer is always 0. So no work is done. You can be sweating like hell pushing the wall until you break your backbone, but you still, according to physics, not doing any work. Okay, so we don't have to pay you any money for that. Alright, number 7. 7 is a roller coaster. Okay, a roller coaster. So look at the roller coaster here. A ball shown in a figure above is released from rest at the highest point A. Assume no friction, so compute the speed of the ball at point B. B is the lowest part. Okay, we re-copy that diagram. Okay, lowest point, and then after that go to the next higher point, and then after that go to quite a constant surface here. Alright, something like that. And B is the lowest point. Okay, so we have ball in a different location. A here is A, B is here, and then C at the top of the second highest point, and then D is a plateau at the horizontal surface again. Now we are given the height. Okay, this one is 45 meter, so B is at the lowest part. Okay, and then D here, okay, this one is given as H unknown, but we know C also. C is 40 meter. Okay, 40 meter. Now we assume that each of them have their own velocity. Okay, at different location they have their own velocity. So we call this one VA. This one is VB. This is VC. This is VD. Alright, we just follow according to the subscript. Now compute the speed of ball at point B. Now what law are we going to use? Okay, we can use a law of conservation of energy. Okay, or you can use work energy theorem if you want, but that is a little bit more complicated. So we're going to use law of conservation of energy. Okay, what does that law say? The total energy at point A must equal to the total energy at point B. Now, what energy are we talking about? This is a mechanical system, so we have mechanical energy, which is the kinetic or the potential energy at point A plus the kinetic energy at point A must equal to the potential energy. Okay, must equal to the potential energy at B plus kinetic energy at B. Now, if you look carefully, A is being released. Okay, A is being released. Yeah, so that means initially, the kinetic energy is 0. But by the time it reaches B, it is at the lowest point. So the potential energy is 0. So now we have a very simple equation to solve. This one is now mgHa. Okay, HA is the height of A from the ground level. This is supposed to be the ground level, the lowest part. And this one is half mvb squared. Alright. So we can cancel the m. Okay, so now our value for the VB is equal to square root 2GHA. Okay, so we put in the value and see what we get. 9.81, and then the height is 45 meter. Okay, so 2 times 9.81 times 45, and then square root. Okay, 29.7, almost 30. So that is the speed. 29.7 meter per second. Okay, next. So that is the first one. Number two is compute the height h if the speed at point D is 22. So you are given the speed at D is 22.15 meter per second. So it's the same story here, you see. You can start from A. Okay, everywhere A, B, C, D, you see, their total energy will be the same because the surface is smooth. Okay, no friction involved. So again, we can use law of conservation of energy that says that the total energy, okay, at A must equal to the total energy at D. And here we know that we have potential energy at A plus our kinetic energy at A must equal to potential energy at D plus kinetic energy at D. Okay, so we know one thing here is, okay, our this one potential kinetic energy at A is equal to 0, but D is somewhere in between here, so it got both energy here. So we open up the equation here. This one is mgHa is equal to mgh. Okay, this is a h plus half mvd squared. Okay, so we can cancel the m here, and now we can calculate the height here. So the height is equal to this one, yeah, this one is equal to so it is GHA minus half VD square divided by G. Okay, alright, correct, huh? GHA minus half VD square divided by G here, or we can simplify further, G divided by G, so we're going to have HA minus VD square over 2G. That's the one. Okay, that's the one. Okay, our HA is 45, velocity also given 22.15 square divided by 2 times 9.81. Okay, so let's check. We have 45 minus this one 22.15 square, and then divide by this 2 times 9.81. See what happened? 19.99, so it's roughly 20.0 meter. Okay, 20.0 meter. Alright, so that is question number 7. Next one. Question number 8. State the SI unit for work. Whoa. The work is F.S. Okay, so the SI unit for work is equal to Newton meter, or this one is also equivalent to Joule. Alright, that's it. That is number 8. Okay, number 9. A 0.145 kg baseball is thrown straight upwards with initial speed 17 from a height of 1.6 meter. By ignoring the air resistance, compute the total mechanical energy at the maximum height if the potential energy at the ground level is 0. Alright, so we have ground surface, okay, ground level here. The ball is released from a height. Okay, this height here is 1.6 meter. Okay, 1.6 meter. So you launch with a velocity u is equal to 17 meter per second, and it will reach a maximum height. By the time it reaches the maximum height, the v is equal to 0. That is what we know when we do free fall question. Okay, the question asks for, by ignoring, one more thing, the mass is 0.145 kg. Okay, 0.145 kg. By ignoring the air resistance, compute the total mechanical energy at the maximum height if the potential energy at the ground level is 0. So what we need to calculate here is how high does it go, or actually we don't have to, because you already know if there's no friction, whatever energy you have here is the same as the one above. But the question asks for the total mechanical energy, so we have to include the potential energy when it is still at the launching point. So I will call this level A, and this level here level B. Okay, so we start with the law of conservation of energy. So the total energy at point A must equal to the total energy at point B. So we don't need to go further to go and find the maximum height. We use energy concept, is much easier. So the total energy here is what? The total energy here, okay, which is equal to only two here. One is potential, see or not? Potential, which is 1.6 meters. So we have potential energy at A plus what we call that, kinetic energy at point A. Okay, kinetic energy at point A, and this is the total mechanical energy at B. So we can straight away calculate our total kinetic total energy here, mgh. Okay, mgh, this is a potential 1.6 plus half mv squared. Okay, so we can calculate now. 9.81, height is 1.6 plus half 0.145, and then velocity is 17 square. Okay, that is what we get. So 0.145 times 9.81 times 1.6, okay, and then plus 0.5 times 0.145 times 17 square. Okay, we got 23, okay, 23.2 joule of energy. Okay, 23.2 joule of energy. Okay, now next one is the change in kinetic energy as the ball reaches the maximum height. How much changes? You lost, right? Okay. So the changes will be this, because when the object, okay, is launched from here, it has kinetic energy here. By the time it reaches the maximum height, it lost all the kinetic energy. So the changes, okay, in the kinetic energy is equal to the final kinetic energy minus the initial. Okay, but we know that final is 0, right? By the time reach here, the kinetic energy is 0. So initial kinetic energy is here only. So I have half m u square. Okay, and that value is we put in a value. See what do we get here? Negative half 0.145 times 17 square, and see that we have 0.5 times 0.145 times 17 square. We got negative 20.95 joule. Okay, loss. It lost that much. All right. So that is our question number 9. Okay, number 9. Yeah. Next. Question 10. Define energy. So what is energy? Energy, okay, is the ability of a system to do work. Okay, energy is the ability of a system to do work. All right, simple, just like that. Number 11. Okay, 11 is a 0.5 kg box slides 70 centimeter in a straight line along a horizontal tabletop with an initial velocity 20 and comes to rest. Compute the average frictional force, okay, that retard its motion. Okay, so we have an object on the surface, okay, and then after it slide for a certain distance, okay, it come to a stop. All right, so that is initial velocity of 20. Okay, if you look carefully, that is 20 cm, okay, per second, right? So initial velocity is 20 cm per, okay, centimeter. It slides 70 centimeter. So that is the displacement, which is 70 centimeter, and the mass of the box is 0.50 kg. Okay, so calculate the, what we call that, the retarding force, frictional force, averagely. So by the time it reaches here, v is equal to 0. So now you have u, you have v, you have s. You can calculate the acceleration using this equation. Okay, this is 0, and this is 20 centimeter per second, change to meter per second, 0.2, okay, square, plus 2a and 0.7. All right, so here you get a. Okay, so you calculate 0.2 square, divide by 2 times 0.7, so you got 0.0286. 0.0286, that is meter per second per second. So now, according to Newton's second law, special case, F is equal to ma. So this is a friction. Okay, is equal to the mass 0.50 multiplied by 0.0286 negative. So we use this one, multiply 0.5. So we got negative 0.0143 Newton. Okay, 0.0143 Newton. That is friction. Okay, friction, yeah. Okay, that's it. That is question number 11. Next, question 12. Question 12 is a pulley system. There is a pulley system. Okay, pulley system. Alright. So there is an object, a box hanging at a height of 10 meter. Okay, the height is 10 meter. And there is a string pulling with a force R. Alright, we look at the question first. A force R is needed to move a box of mass 3 kg. Okay, this is 3 kg to a height of 10 meter at a constant speed, no acceleration, using a smooth pulley, no friction, as presented in the figure above. Compute the work done by the force R. Okay, so now in this case, you remember work energy theorem, as we discussed just now. Work energy theorem states that any work done on the system is equal to the change in kinetic energy of the system. And I did say after that, you can actually apply that not only to kinetic energy, but to potential energy as well, right? Okay, so from here, when you are pulling here, you actually apply a force. Okay, apply a force here. What is the force here? This force is your force R. Okay, is your force R. Now, in order to pick up this thing, this one must be at least equal or larger than the weight of the object. When you are equal, then the object will move at constant speed. When you are larger, then the object will, what we call that, accelerate. So here we got two statements. If your R is equal to mg, then A is equal to 0, not accelerating. Then if your R is larger than mg, then your A is larger than 0. But we don't want the second one, because the question say it actually moves up constant speed. So we're going to choose the first one. The force must equal to mg. Okay, to have to move up constantly. Okay, constantly velocity, at constant velocity, the R is equal to mg. Alright, now we know that there is a force. Okay, and then you want to calculate work done. Okay, you want to calculate the work done. So the work done is equal to what? Is equal to F dot S, right? Okay, F dot S. So the force R is upwards. So I put R, and then displacement is upward also. This is your displacement, see? I use orange color, the displacement of the box. So that is the displacement. So they're in the same direction, so the angle between them is 0. So now we have Rs cosine 0. Okay, and your R is equal to mg. So we have mgs, cosine 0 is equal to 1. So m is 3 kg, g is 9.81, and then displacement is 10. So we have 3 times 9.81 times 10. So we have 294.3. Okay, 294.3 joule of work done by the R. Okay, all right, so that is question 12. Next, 13, define power. So power can have a few definitions. Two definitions we can think of. Power is defined to be, okay, number 1, you can either define number 1 or number 2, or you want to write both also can. Power is defined to be the rate of work done. Number 1. Or B, the rate of transform of energy from one energy to the next, how fast it is changing. Okay, how fast it is changing. That is power. So our power, you can write down, is equal to dW dt or equal to dE dt, or you can use delta if you want. This one is more in the calculus form. Okay, next, question 14. So question 14, again sliding. Sabrina. Anyone call Sabrina here? Sabrina pull. Okay, Sabrina pull something here. Wait. Okay, question 14. We have a Sabrina pull a 25 kg block with a force F at 30 degrees above the horizontal line. Shown in figure above, the block move, okay, with a constant acceleration 2.5. The coefficient of kinetic friction between the surface and the block is 0.15. Okay, this is a accelerated system. Floor, and Sabrina is pulling a box. Okay, at an angle of 30 degrees with a force of not mentioned, sorry, force is not known. Okay, we don't know the force, but the mass is given. The mass of the mass is 25 kg. Okay, mass is 25 kg, and it is accelerating. The system is accelerating A of 2.5 meter per second, and between the surface we have mu is equal to 0.15. Okay, compute the magnitude of the pulling force F applied by Sabrina on the blocks. Well, this is not a guided question, so there's a lot to do here. Now, first thing, we split the force F into its component, okay, like one of the previous question before. So this component here is the one that accelerates, so we call it Fx, and this one is the one that's going to change the normal reaction, reduce the normal reaction. Okay, and then here we have the weight of the object, W equal to mg, and then the normal reaction from the surface, N. And other than that, we also have friction, F. Okay, friction F. So friction F depends on the N, but don't forget, how do we get our N? Okay, this is how we get our N. The total vertical forces must equal to 0. We assume that the box, even though they have a component force like this, but the box is not moving up and down. So we have N plus Fy minus W equal to 0. So the N is again W minus Fy, and mg minus your Fy if this angle is given. Okay, it is 30 degree, I believe. 30 degree. So it is F sine theta. So that is our N value. Okay, that is our N. Now, the next thing is we're going to put the N into the friction formula. Okay, the friction is equal to mu N. So we have mu mg minus F sine theta. We calculate later. Yeah, there's the F. All right. So you are asked to calculate the force F. Okay. So what we know is we only know the Fx is horizontal with the displacement. So it is accelerated at 2.5 meter per second. So we are going to use Newton's second law to calculate the A. Okay, to calculate use a law to help us to find the net force. Okay, to find the net force. So first, we know that the net force is equal to horizontally is equal to ma. We know the mass, we know the m, but our net force here is Fx minus friction is equal to ma. Alright, so our Fx also is equal to F cosine theta. So our F cosine theta minus F is equal to ma. So from here we can get our value F here. So this is first one. Okay, so check first, so we can calculate this later on. Okay, never mind, we put this one like that first. We just keep our equation number 1. Okay, next one. We are given A is equal to 2.5 meter per second and the mass of the box is 25 kg. So according to Newton's law, the total force is equal to MA. So we can calculate the net force here, F. Okay, this is a net force. I put total, yeah, total net force is equal to 25 times 2.5. So you have I believe it's 600 plus. Okay, 2.5 times 25. Sorry, 62.5. Okay, 62.5 Newton. Right, 62.5 Newton. We're going to put this whole thing. This whole thing is here. Okay, MA is equal to this. So we have F cosine 30 minus the friction. This one. This one here. So we have minus, or we move the friction over there is easier. So this one is equal to friction, which is equal to mu mg minus F sine 30, okay, and then plus this 62.5, okay, plus that 62.5. Okay, so we simplify the equation first. We have F, this one is square root 3 over 2 is equal to 0.15, m is 25 times z 9.81, and then minus 0.15 times F, this is half, okay, plus 62.5. Okay, so we simplify this, square root 3, okay, divide by 2, so we're going to get this, and then we sum up with this, yeah. Okay, we sum up with this one. Okay, that one will be plus 0.15 divided by 2. Okay, 0.941 F and everything here. Okay, 0.15 times 9.81 times 25. Okay, and then plus 62.5. Right, you have 99.29. So the force should be divided by 0.941. Okay, so it is 105. Okay, 105.5 Newton. Okay, 105.5 Newton. All right, so there is a force. Okay, H3. There's a force F. Okay, complicated, yeah. Next part. This is number 1. Next part is the work done by Sabrina if we move the blocks a distance of 100 by Sabrina, yeah, not the box, by Sabrina. So if it is by Sabrina, then we have to consider only the force applied by Sabrina, which is 105.51. Okay, this is the second part, page number 4. Okay, work done by Sabrina is the force F dot distance, this travel. Correct? Okay, so is the distance travel given? Not given, so you have to let's have a look here. If from rest, we assume that it is from rest, okay, it moves with a constant acceleration of 2.5, and then we already calculated the force applied by Sabrina. And then oh yeah, if we move a block 100 meter, okay, done already. So we have the force, okay, work done. So let's have a look. There is Fs cosine theta. The force applied just now is 105.51, and then the displacement is 100, and then the angle between them is 30 degrees, correct? 30 degrees. Okay, let's check. Is it 9,000 plus? 105.51 times 100 times cosine 30. Okay, 9140 joule. Okay, 9140 joule. All right. Okay, done. 14, 15. Okay, question 15. Roller coaster question. So we have roller coaster. Alright, different height. Okay, we have a ball at different location here, B and C. So this is A, this is B and C here, have their own different height. Okay, this one is 1.5 meter. I call this one HA, 0.8 meter, and this is 2.0 meter, right? And their velocity we accordingly to their subscript VA, VB, and VC. Okay, consider a ball of mass 4 kg. The mass of the rolling ball is 4 kg. Rolling on a smooth surface. Okay, the ball moving is an initial velocity starting here 7.5. Okay, dA is 7.5 meter per second. Compute speed at point B. Okay, so again, what we are using here is total energy. So according to the law of conservation of energy, between point A and B, we know that total energy at A must equal to total energy at B, which is potential energy at A must equal to kinetic and plus kinetic energy. Okay, wait. Potential energy A plus kinetic energy at A must equal to potential energy at B plus kinetic energy at B. Okay. So all energy are there. So we just need to put the equation in the correct place. Okay, this is mgHA plus half mVA square equal to mgHB plus half mVB square. Okay. So we need to find the speed of B. So that's the one. So before that, we can cancel the m. Okay, m all cancel. So we can multiply by 2 also, so that the equation become 2GHA. This one become VA square equal to 2GHB plus VB square. Okay, so we can have VB square is equal to VA square plus 2GHA minus HB. Okay, or square root everything. Alright, so you can put in a value. This is a 7.5 square plus 2 times 9.81. HA is 1.5 minus 0.8 square root. Okay, so that is what we get. Okay, now 2 times 9.81 times the difference between them, 8. Okay, and then plus 7.5 square. So we got this. After that, square root everything. So the 8.37 meter per second. Okay, 8.37 meter per second. Next one, number 2. This is number 1. So number 2 is will the ball reach C? Show your calculation to prove your answer. Will it reach C? Okay, let's have a look. We calculate the total what we call it, total energy at C. Assume that, okay, assume that, okay, it stop at C. Okay, that is the minimum condition. Okay, the minimum condition. Yeah? So what we need is both sides the same or not. First, we calculate the total energy at A. Okay, total energy at A is equal to the potential energy at A plus the kinetic energy at A. Okay, that's what we calculate here. This is mgHA plus half mVA square. So we put in the value here for 9.81 and then 1.5 plus half. Mass is 4 kg and then velocity 7.5 square. Okay, that is our value. Now we have 4 times 9.81 times 1.5. This is what we get. Okay, and then plus 0.5 times 4 times this one 7.5 square. Okay, 171. Okay, 0.36 joule. That's the total energy here. If the total energy at C, okay, if the total energy at C, in this case we assume it stopped there, the ball reached there, stopped there, we only have mgh, okay, mgh. So it is 4, 9.81, and then multiply by height 2 meter. Okay, let's see whether it can reach there or not. 4 times 9.81 times 2. Oh, no problem. It can reach there definitely. 78.48 joule. Okay. So let's assume like this. This one we don't know. Okay? This one we don't know here. You see, kinetic energy at C. So we have plus kinetic energy at C, kinetic energy at C. So when we compare, okay, law of conservation of energy, your total energy at C must equal to total energy at A, right? So this one is 78.48 plus kinetic energy at C is equal to 171.36. Your kinetic energy at C is a positive value. Okay, 36. Okay, positive 92.88 joule. Okay, so it can reach C with extra kinetic energy. No problem. Okay, you can reach there with extra kinetic energy. All right. My goodness, my aircon spoiled already. Now I'm sweating like hell. Okay, 16. Explain the principle of conservation of mechanical energy. Okay, so principle of conservation, okay, or law. Principle of conservation of mechanical energy, okay, states that the total potential and kinetic energies, okay, at any point is a constant. Okay, so that means potential energy plus your kinetic energy is equal to a constant K. So if that's the case, then at any 2 point, P1 plus EK1 must equal to EP2 plus EK2 and so on. Alright, that is a principle. Yeah. Okay, next one, 17. Is a figure above shows a 15 kg toolbox is dragged horizontally for a distance of 25 meter. Okay, 25 meter dragging, you drag. So assume that it's been dragged. Okay, with a force F. The force looks horizontal, and then it's been dragged for a displacement of 25 meter. Okay. So given the force F applied to the toolbox is 65 Newton, and the friction, okay, you're given friction 25 Newton. Okay, the friction is 25 Newton. Alright. So explain the work energy theorem. Okay, work energy theorem we already discussed, right? Work energy theorem state that, okay, you refer to question 5. Okay, refer to question 5. Compute the work done by the force. Find the work done by the friction. Okay, when they say force, this one. So work done by the force is equal to F dot S. So in this case will be Fs cosine 0 because they're in the same direction. So we have 65 times 25. So answer will be 65 times 25, 1625. Okay. 1625 joule. There's a work done by the applied force, big F. See, work done by friction, small f, is a F dot S. This one is Fs cosine 180 or negative Fs, right? So negative friction is 25, so answer is negative 625 joule. Okay, negative 625 joule. Next, D. Calculate the total work done. Well, the total work done is equal to all the work done you have calculated. So in this case will be 1625 plus negative 625. So answer is 1000 joule only. Okay, 1000 joule. Okay, so that's it for our tutorial. Oh, still have, sorry, I thought finished already. Okay, continue. Page number 5. Page 5, question 18. Okay, question 18 here. Figure above shows a boy that don't look like a boy, look like an adult, lifting a 6 kg box with a 65 Newton force to a height of 0.5 meter above the floor. Sketch a free body diagram to show all forces acting on the box. Okay, so we have a box. Box only here. So the force number 1 is this one, weight, mg. Okay, and then a force is applied to it, 65. Okay, a force of 65 Newton, right, lifting. And of course, because the box is 6 kg, at most it is only 60 Newton, so that means it's going to experience an acceleration. Okay, accelerate up. So there is a accelerating force. The net force will be 65 minus 60, so roughly about 5 Newton. Okay, now A. Sketch a free body diagram, already done. B. Compute the work done by the boy to lift the box. Okay, so you see it lift it up to 0.5 meter. Okay, applying a force 6.5 meter. See, so the work done by the force F is the force F dot displacement, and it is Fs cosine 0. So it is 65 multiplied 0.5. So you got this answer. Okay, 65 times 0.5. So you got 32.5 joule. 32.5 joule of work done. Next one, C. C is compute the work done by the gravity on the box. Okay, gravity is because of the mg. Okay, because of the mg here. So by the gravity is equal to the weight dot s. But the weight's downwards, so the angle between them is 180 degrees, so negative ws, or negative mgs. Mass 6 kg times 9.81 times 0.5. Okay, so 6 times 9.81 times 0.5, you got 29.43. 29.43 joule. Gravity do the negative work here. Alright, next. Compute the net work done. Okay, sum up everything. Net work done, D. Total net is equal to work done by the force F, work done by the gravity. So sum up everything. Just the difference between them, 32.5 minus 29.43, so we got 3.07. Okay, joule, 3.07 joule. Yeah, okay. Next question 19. Identify 2 types of energy that involve when a ball is dropped from a certain height. 2 types of energy that involve. Okay, identify only. We draw a ball coming down, okay, with a certain velocity v. So it's coming down. Okay, coming down from a certain height. Okay, certain height. So when you have a certain height, you always refer to potential energy, gravitational potential energy. So number 1 is potential energy, which is mgh, mass and the h. And then number 2, kinetic energy, which is half mv squared. Right? That's it. 20. express the equation of power in terms of work done on an object. Express the equation of power in terms of work done on an object. Well, we already know that just now. Power is equal to the work, what we call that, the rate of work done, like that. That's the one. Work done per unit time. dW dt, or W over T, or delta W over delta T. That's one. Okay. Next one. Last one. 21. A 50 kg elevator is pulled upward with a tensional force of 550 newtons for a distance of 10 meters in 7 seconds. Elevator, okay, pulled up by a force, okay, tensional force up. The tension is equal to 550 newtons, and it moved up a distance h of 10 meters, okay, in 7 seconds time. Okay, in 7 seconds time. So A, compute the work done by the tensional force. Okay, work done by the tension is equal to the tension times displacement. So the tension is upward, displacement is upwards. So we have Ts cosine 0. So we have 550 times 10, 5,500 joule. Okay, next B, work done by the gravitational force. Okay, this is a gravitational force, mg or W. Okay, W equal to mg. So also move up, but against. This one is going to get negative always. So work done. So you have this Ws cosine 180. So negative Ws or negative mgs. So negative, it is 50 kg, 9.81 times 10. Okay, times 10 meter also. 50 times 9.81 times 10. So you have negative 4905 joule. Okay, negative 4905 joule. Yeah. Last one, total work done. Okay, total or net work done is the work done by the tension plus the work done by gravity. Just minus them. So you have this minus 5500. So you have 595 joule. Okay, so that's it. The tutorial for number 5 uploads. Okay, now, okay, bye bye.